So we will introduce a specific type of martingale and examples of such martingale. So most of our application will deal with the following martingale. Suppose that there are random variables x1 to xn, which are not necessarily independent. So those can be depend each other, it doesn't matter. And if you consider each xi, then it has a value in vi. So vi could be arbitrary set. So random variable having values which is not necessarily in real number. And let f be a function which is defined on the product of this v1 to vn and having value in real number. And let yi be the expectation of this function f. And conditioning on the first I event. And again, if I write in this way, this actually means, no matter how we condition on here, then this sequence of random variable y0 to yn actually forms a martingale, and this is called either the Doom martingale or the exposure martingale. For example, the number of heads that we get from the coin flipping. No, let's consider in this way. The gambler, whether earns or lose, each of xi is a random variable indicating whether gambler win or lose on the ith round. To be more specific, this is a coin flip. And say V1, Vi is a head or tail. So each coin flip has head or tail, and this function f is adding 1 for each head and adding -1 for each tail. So that's our function. And this yi is exactly, not exactly, but so in that case we can consider this yi as this. Then what is this yi in the above setup? If we know say x1 to xi are say head and head. Let's assume that all of them are head. Then x1 to xi are all head. And xi plus 1 to xin, what are those? Those are, with probably half their head, probability half their tail. And then in this setup, f adds or subtract. So on expectation, they are half times say 1 plus 1 minus 1 plus you use the linearity of expectation to compute. Then they are all just 0. So yi is, if all of them are head, it's just I. And assuming this, I mean, you can actually check that this is a martingale because expectation of what's yi plus 1. Then, by the formula for expectation, it's a summation of two things. So xi plus 1 could be head or tail with the probability half. If it is also head, then by the same logic, yi plus 1 is I plus 1. And if it is tail, then by the same computation, this is I minus 1. So this summation is same as yi. So it's, you can check that this is a martingale. Again, you can consider this on the first example of just counting the number of heads. Number of heads is 0 or -1. So that was not martingale before you actually subtract this fi. But it doesn't matter here. So as long as, I mean, you take this expectation, it becomes martingale because what's y0? y0 is expectation of fx1 to xn, each x1 to xn, assuming nothing. Each x1 to xn is with probability half contributing 1 and probability half contributing 0. We just count the number of heads. So this is half n. And yi is, say, x1 to xi are given. And then let's say s of them are heads. Then this is s plus half times m minus s. I mean, we condition on, I mean, s of them and being heads. And then rest of them are, again, by same logic, contributing half. So you get this. And what's yi plus 1? yi plus 1 is, again, with probability half. Next one is head. Then it's you condition on x1 to xi and xi plus 1. And this is head in this event. And this time this is tail. And the upper one is by the same calculation. This is sorry, so yeah, so expectation of yi plus 1 is yi. So this is a martingale. Similarly, you can actually prove that, I mean, it's not difficult to also check that this actually forms a martingale. Because what's expectation of yi plus 1? Which is summation of the, I mean, f of x1 to xn and probability that x1 to sorry, I actually should have conditioned this on yi. So let's write it this way. So you condition on yi. So actually, I mean, here its definition is we condition on the all previous event, but let's just Okay, let's just condition on the all previous event. You can actually write this as a f of x1 to say so let's just fix x0 x1 to xi. Then this is actually a stronger statement. If we know this is same as expectation of this is yi, which is actually f of expectation of fx1 to xn, conditioning on the same one here. If we know this, then if we take the y0 to yi, then that's also same. You can actually show this because conditioning on this is you condition on the events which are union of many events, union of many of these. So if you fix these numbers, this number something, this number something. So for example, y1 is 1, y2 is 2, y3 is say 0. Then there are collection of x1 to xi which yields exactly this number. So there could be more than one such sequence, but you consider it a collection of such sequence. In that collection, for each sequence, if you have this equality, then you take the expectation over all those sequences, then the above one is also true. So if we just prove this equality, then that implies that it is a martingale. Then, depending on the probability distribution, you actually, can compute the probability of you get specific sequence where the first I sequence are same and then later sequence. But what's this? This is nothing but the probability of you get xi plus 1, assuming this, and probability that you get x1 to xn, assuming x1 to xi and xi plus 1. So again, when I write this, this is actually xi plus 1 equal some small xi plus 1, and you consider summation over all this one and the later one as well. Give me a moment. What was I doing? This is actually yi. Sorry that I was a bit confused myself. This is yi. Yeah, this is definition of yi, which is expectation of f x1 to xn. Conditioning x1 to xi. Yeah. But what's this now? So if you pull this out, and this is actually summation over all this, but which is double summation. Summation can be broken into two. One is over xi plus 1, and one is over the remaining one. And if you pull that out, then this is summation over xi plus 1, probability that you get xi plus 1. And summation of xi plus x2 to xn, f x1 to xn, probability that you get this sequence over the choice of first I plus 1 numbers. This is exactly yi plus 1. And this is the probability that you get this yi plus 1, which is expectation of, if you rewrite it one more time, the probability you get xi plus 1, to be more precise, then this is expectation of yi plus 1. Yeah, sorry that I was confused a bit earlier, but this verifies that this exposure martingale is always a martingale. Let's consider some examples. So there are several martingale that we will frequently use. So one is the edge exposure martingale. So we consider the random graph. G and P. And we enumerate the pairs of vertices. So this E1 to EMB an enumeration of pairs in here, all possible pair, and let that be any graph theoretic function. And let G be the random graph drawn from this GMP. So in this probability distribution, we choose a graph G, and let EI be the indicator random variable, which is 1 or 0. 1 if EI is in this G, and 0 otherwise. Let's say let Xi be the edge exposure martingale. So again, exposure martingale depending on the first I edges. So the first I edges are determined. First I pairs are determined whether they are edges or not. But the rest of them we don't know yet. At that moment, you can compute the expectation of this F0. Then this is a martingale. And it is called edge exposure martingale. So let's consider, say, an example. We consider the chromatic number on G3 half, say. So G3 half consists of the A graph on 3 vertices. Say this is 1, 2, 3 vertices. You can have one of these, say, A graphs. Let me use more space. 1, 2, 3, 4, 5, 6, 8. So these A graphs are having probability 1/8 each. So let's consider, let's give names in this way. One, two, three. So 1, 2, 1, 3, 2, 3. So what's x0? This is chromatic number 3, 2, 2, 2, 2, 2, 2, 1. Then if you take the expectation over all things, then this is expectation of chromatic number of G is you multiply 1 over 8 each and then add together, then you get 2. And so this is E1, this is E2, E3. If E1 is 1, I1 is 1, let's write it this way. If I1 is 1 or I1 is 0, if I1 is 1, that means we consider these 4 graphs while these 4 graphs are not considered. So you take these 4, you condition on these 4, so each of them has a priority 1/4, and you consider the expectation, then you get 2.25. And if I1 is 0, then here you have these 4 edges are not there, so you condition on these 4 graphs. Each of them has a priority 1/4. So your x1 has value this. And again, the second one, 1, 3, after this, if the second one is 1, then you are conditioning on those two, so 2.5. And the other case is conditioning on these two, 2. And similarly here, again 2, here again 1. So that's your value of x2. And x3 is if all 3 things are revealed, you could get this. So you see that the expectation of x1 is same as 2, expectation of x2 is same as x1, expectation of x3 is same as x2. So this is a martingale, and this is called edge exposure martingale. And there is also vertex exposure martingale. So again, consider the random graph G and P, and F graph theoretic function, and V1 to Vn be an enumeration of vertices. Which is a bracket n. And now again, G is the graph drawn from the GMP, and let I super I be the vector of length I minus 1. This is the J's coordinate is the indicator random variable for the event Vi and Vj are on edge. Say is 1 or 0 if Vi, Vj is on edge of G, and if not, it's 0. In other words, you before edge exposure martingale, you expose one edge by one edge. But now, first step you expose nothing, and second step you expose this one edge. Third step, you expose these two edges. Fourth step, you expose these three edges. Fifth step, you expose these four edges. Each time you expose all the edges incident with your current vertex to the or previous vertex. And you take the expectation of your function, then that's the vertex exposure martingale. So these are the, martingale that we usually deal with. And now, again, the reason why we are learning about this martingale is that once we have a martingale, we can actually, show some tight concentration results, meaning that the martingale xn is very close to certain, it's the number x0 with high probability. But for that, we need one more condition. So as I mentioned before, here, not just first one, but we also want to make sure that the second one. The second one is related to the following. So we want to show tight concentration result, but we consider say x0 is 0 and x1 we want to show that this is close to 0, close to x0, which is 0. But this could be that the large number m or negative m with probability half and the other half. In that case, it is martingale. Its expectation is 0. But it can be, the actual value is either m or negative m, which is far from 0. So in that case, we cannot show the concentration result. So we want to kind of avoid this. And we can actually show that once we avoid this, then we have this martingale. Then by the definition of martingale, the xi plus 1 is somewhat tight from xi, so that it has tendency to not to deviate. So you can actually show concentration. That tendency is strong, so that with high probability, the martingale cannot be deviated too much from x0. So let x0 to xm be a martingale. And xi plus 1 and xi are, in any case, the difference is at most ci for all I. So ci is some constant. So for example, in the coin flipping one, our martingale does not change more than 1. It's not difficult to actually check. Or in this case also, when you add or subtract h, the change, the expectation, the value xi does not change more than 1. So in that case, those ci can be 1. Then for given lambda, the probability that the difference, xm is far from x0, the distance is more than lambda, is smaller than the exponential function. Which, decays exponentially as lambda grows. So this Azimuth inequality, or Azimuth-Hofstee inequality, is what they are calling. I mean, this ensures that we can get the tight concentration result. So in next video, we will prove this inequality.